Now, if a random process x of t is stationary, then, well, we said the definition applies for any choice of k, any choice of the number of samples. Assume that we have just one sample at t. So that means whenever I shift that time instant t by any amount tau, okay, the distribution should stay the same. That means the distribution of any observation at time t should be equal to the distribution of any observation at t plus tau for any for any value of tau. Therefore, we conclude that the distribution, in fact, the distribution of one observation should not be time dependent. Okay, this is very important. When you have a stationary random process, that means the distribution of one observation is independent of time. Okay. So essentially, this means all observations must be identically distributed. Wherever you observe the random process, all of them should have the same identical distribution. But I'm not saying IID, be careful. They can be independent or they can be dependent. Okay? What we are saying is they must have identical distributions. Observe at any time instant, the distribution should be the same. Okay? And when you have this, it's easy to see that the expected value of this random process should be also independent of time, because now this is independent of time. And since I'm just multiplying this with parameter x and integrating it over the sample space of the random process, there is nothing time dependent here. So the result should be time independent. Okay, so the expected value of a stationary random process is constant, doesn't depend on time. Similarly with variance, by definition, the variance is, well, this is the definition. Since we know that the expected value is independent of time and the PDF is also independent of time, obviously the result, which is variance, should be independent of time. Furthermore, if you look at two observations and consider their joint distribution, okay, x of t1, x of t2, we know that any shift amount should not change the joint distribution. Therefore, if I shift the origin to t1, that means this time instant will become the origin 0. Therefore, t2 should become t2 minus t1, okay? By stationarity, this should hold. Okay, that means the second order CDF of a stationary process, the second order in the sense that I'm observing two instances, it depends only on time difference between the samples and not on the particular instance of the observations. This is a very typical property, a very significant property of stationary random processes. If you observe it at two time instances, the specific values of these instances are not important. What is important is the separation between them, okay? Now, when you have this, if you just write the autocorrelation and autocovariance functions, it's just x1 times x2 times the joint PDF at these points, because I'm actually computing the expectation of x1, sorry, xt1 and xt2 by the definition of autocorrelation. And since this doesn't depend on time, this doesn't depend on time, and this thing, this joint PDF, does not depend on T1 and T2 separately, but only on their difference. X of T2, T2 minus T1. Okay, so this means the autocorrelation function Rx of T1 and T2, if you remember, the autocorrelation function in general depends on the two time instants separately. But in this case, if you have a stationary random process, that means the autocorrelation function will not depend on T1 and T2 separately, but only on their difference. Same goes for autocovariance. And typically, we denote this time difference, T2 minus T1, with tau.